something is wrong with a visitor from another star. 3i Atlas skimmed the sun, blasted away a huge share of its mass, and by every textbook it should be dragging a bright, screaming tail. Instead, telescopes saw a compact glow, a fuzzy ball where chaos should spill across space. China's Mars orbiter, Tianwen-1, even captured the closest images we will likely ever get. Still no obvious tail, no streaming debris, just silence. Tonight we chase the missing tail and what it might mean. Before we dive in, tap like and subscribe so you do not miss the next twist. Here is the paradox in plain language. When a comet rushes near the sun, sunlight and the solar wind heat its surface and blast loose gas and dust. Radiation pressure shoves that material away from the sun, carving a graceful tail that points anti-solar, meaning away from the glare. The closer the pass, the stronger the outflow, the bigger the tail. With 3i Atlas, the numbers are not whispers. Astronomers tracked a small but measurable push on its motion that cannot be explained by gravity alone. That extra push signals vigorous outgassing. Conservation of momentum says the nucleus must have shrugged off a lot of mass to generate that force. How much is a lot? The trajectory solution implies at least 13% of the body's mass fled into space during the days around its closest approach. For a nucleus, a few kilometers wide, that translates into billions of tons of material. Enough dust to paint a river of light across the sky. Enough gas to fill a coma that swells and brightens and drags a clear tail behind it. That is not a dramatic flourish. It is basic bookkeeping. The mass leaves the nucleus. The flow gets pushed by sunlight. The tail appears where every comet tail appears. Now look at what the cameras actually saw. On November 5, after weeks of quiet effort from Mars orbit, Tianwen-1 released black and white frames of 3i Atlas. The images showed a compact sphere with a diffuse halo, the coma, stretched across thousands of kilometers, beautiful and maddening. Because there was no crisp streamer splayed out in the anti-solar direction, no obvious sign of 4 billion tons of dust and gas sprinting away from the Sunday. On the same night, ground-based telescopes echoed the view. A fuzzy glow, a neat little coma, no tail that shouts I just shed 13% of my mass. That is why the room went quiet in astronomy circles. You do not get to pick and choose between the math and the images. The path through space says a force acted. The lack of an obvious tail says the usual reason for that force is hiding, or missing, or masquerading as something else. Maybe the material was almost all gas, thin and transparent against the background, producing thrust without much visible dust. Maybe geometry hid a narrow tail by aligning it edge-on. Maybe the outflow happened in spurts that cancelled out the usual shape. Each maybe is worth testing. Before we race down the list of explanations, we have to sit with the most important feeling of all: curiosity. You and I are watching a rule that has held for thousands of observed comets wobble under the weight of a single stubborn dataset. We have the closest look from Mars orbit. We have timing around perihelion at just under 1 astronomical unit from the Sunday. We have a measured nudge that implies serious mass loss. And we have images that refuse to pay the bill that physics has placed on the table. That is not a scandal. That is an invitation. Over the next minutes, we will treat this like a shared investigation. We will keep the energy high, but the reasoning careful. We will look at what comets are supposed to do and what this interstellar visitor actually did. We will test baseline physics first, then follow the evidence wherever it leads. If the ordinary answers are strong enough, they will hold. If they are not, we will say so and keep going. That is the deal. Mars had the best seat in the house. While Earth stared into sunlight near perihelion, a quiet spacecraft above the red planet turned its camera away from home ground and toward a faint target sliding across the stars. Tianwen-1 was built to map canyons and dunes, not to chase a dark marble from another star. Yet in early October, the team retasked it, dialed in new tracking rates, and taught a landscape imager to follow a point of light. On November 5, the Chinese Space Agency released what it saw: a compact glow with a broad halo, the closest frames humanity is likely to get of 3i Atlas. Think about what that pivot required. A camera tuned for bright, slow, high-contrast terrain had to find an object only a few kilometers wide, darker than asphalt, moving tens of kilometers every second, and so far away that light took a full minute to cross the gap. The nucleus was roughly 5 to 6 kilometers across. The range was about 18 million miles from the orbiter to the target. At that distance, the comet is not a pebble. It is a dust mote. You must track it smoothly, or it smears across the detector. You must expose just long enough to beat the noise without washing out the coma. You must subtract a star field that never stops drifting. Engineers love this kind of problem. They leaned on gyros and star trackers. They built a pointing plan that predicts where the comet will be, not where it was a moment ago. They adjusted readout timing and stacked multiple exposures to pull a whisper up out of the sensor floor. None of that makes for flashy headlines. It does create trust. When these frames arrived, they were not lucky snapshots. They were proof of control, a demonstration that you can hold a tiny moving target steady from millions of kilometers away. Now fold in the geometry. From Earth, 3I Atlas swept behind the Sun during closest approach. The line from our planet to the comet ran straight through dazzling daylight. Ground telescopes were blind, and even space telescopes near Earth had painful glare to fight. Mars was offset just enough to break that glare. Tianwen 1 slid into a sweet spot, not because someone planned the universe around our curiosity, but because sometimes orbital mechanics hands you a gift if you are ready to use it. Other spacecraft watched as well. Europe's missions at Mars, Mars Express and the Trace Gas Orbiter, recorded the visitor from their own vantage points. Those observations matter. They confirm that this was not a one-off quirk. Yet the Tianwen frames carry a special weight. They were the closest images, by any human machine, nearer than the Hubble Space Telescope and the James Webb Space Telescope could manage during this window. Close does not always mean clear, but it often means you get the first honest look before the details are smeared by distance. What did that honest look show? A blurry sphere surrounded by a diffuse coma that measured thousands of kilometers across. No sharp streamer, tearing away from the Sunday, no bright ribbon pointing into interplanetary space. The silence in those images is the point. If the physics says billions of tons left the surface, a camera this close should see the evidence as a tail. Instead, we see an orderly glow and a neat halo. That is why these frames are more than postcards. They reset expectations. They tell us the missing tail is not just an artifact of long-distance viewing or bad weather over Italy. They tell us the problem followed the comet into the best geometry we had. The closest look was not simply a triumph of engineering. It was a clue, and clues demand the next step. Begin with a picture you can feel. The Sun bakes a dark, porous surface, and the trapped volatiles inside start to boil. Gas bursts from vents and drags fine dust with it. Sunlight and the solar wind then shove that material away from the glare. The result in textbook after textbook is simple. A coma swells around the nucleus and a tail points. Anti-solar, like an arrow of smoke on a windy day. Now swap the metaphor for mechanics. A comet is a natural rocket. When gas and dust shoot off one side, the nucleus gets a tiny push the other way. Astronomers measure that push as a deviation from the path gravity alone would draw. Even if the kick is small from 1 minute to the next, the effect accumulates over days and weeks. Plot the positions on the sky, and you can see the nudge. That nudge is the signature of mass leaving the body. Momentum conservation turns that signature into a bill that must be paid. If the nucleus accelerated a little away from the Sun and a little sideways, then a lot of material had to be thrown overboard to create the matching reaction. For 3I Atlas, the accounting says at least 13% of its mass left during the perihelion passage. Translate that into something you can imagine. Billions of tons in only a few days. That is quarry-scale physics on a cosmic stage. The next step is where visibility enters. Gas can be faint, but dust is bold. Micron-sized grains scatter sunlight well, especially at small angles near the Sunday. That is why ordinary comets blaze into fans and streamers that even modest telescopes can record. If a nucleus throws off a mountain of material, a tail should appear where the solar wind and radiation pressure drive it. The anti-solar direction becomes a compass you can trust. There are wrinkles, and they matter. Comets are lumpy. Vents switch on and off as the body rotates. Diurnal heating can move the active region around the surface like a spotlight. These effects tilt the outflow and can create jets that do not line up perfectly with the sunline. That is how you get a transverse push in the trajectory solution. Yet the geometry still funnels most dust away from the Sun overall. The fine structure may twist. the basic arrow should still point. Consider scale. A nucleus roughly 5 to 6 kilometers wide has a surface area of tens of square kilometers. Even if only patches are active, the sheer energy near one astronomical unit can drive enormous mass flow. The coma grows to thousands of kilometers across. Then the dust feels the sunlight as a steady hand pushing it outward. If you could hover beside the comet, you would see grains lifted, accelerated, and sorted by size into a broad streamer. Now return to what the cameras delivered. A compact coma, no crisp streamer. The anti-solar direction looks quiet. That visual silence must reconcile with the dynamical shout written into the orbit. If almost all the expelled material were gas, the thrust could be strong while the look stays subdued. Carbon monoxide or carbon dioxide jets can carry momentum without leaving much dust behind. That is a real possibility, but it comes with a test. Spectra should reveal abundant gas, and time series should catch a fading signature as the vents relax. Another option is geometry. If the tail lies almost exactly along our line of sight, its width collapses and its surface brightness drops. Edge-on alignment can hide structure that otherwise looks obvious. That too has a test. Different observers at different vantage points should see different shapes. With Tianwen-1 near Mars and ground observers on Earth separated by giant baselines, a pure geometry trick becomes harder to sustain if everyone reports the same compact glow. The physics is not offended by challenges. It invites them. Outgassing must produce a reaction force, and ejected material must go somewhere. If the material is mostly gas, we chase it with spectra. If the tail is aligned, edge-on, we check parallax and viewing angles. If the vents were impulsive and brief, we search for timing that would smear a tail into the background. Step by step, we let the numbers decide which doors stay open. That is why this section matters. It sets the rules of the game before we argue about plays. Near the Sun, a comet is a rocket whether it wants to be or not. And rockets leave fingerprints. The path of 3i Atlas says a powerful hand pushed it. The sky says the usual fingerprint is faint or missing. Physics demands both facts be true at once, and our job is to discover the bridge between them. The first reality check arrived within days of closest approach. On November 5, 2 independent teams released images of 3i Atlas after it had rounded the Sun and should have been unfurling a brilliant streamer. The Virtual Telescope project in Italy and the Naves Observatory in Spain both marked the direction toward the Sun on their frames and traced the anti-solar line where any respectable tail should point. In both datasets, the comet looked the same. A compact glow with a small coma and no obvious tail. 2 observatories, 1 conclusion. The sky was quiet where it should have been loud. Comparisons make or break mysteries, so the Spanish team did something simple and devastating. 2 days earlier, they had photographed a garden-variety comet named Lemon. Same telescope, same operator, similar geometry in the sky. Lemon displayed a crisp plume exactly along the anti-solar axis, a textbook tail that made the physics feel dependable. Place the Lemon frame beside 3i Atlas, and the contrast snaps into focus. One looks like a comet. One refuses the role. That is where viewing geometry steps into the conversation. Could the tail be there yet hidden by perspective? Edge-on alignments can flatten a wide fan into a thin streak whose surface brightness falls below the detection threshold. The easiest way to test that is to look from different angles. Earth-based telescopes and a camera in Mars orbit give us a huge baseline. If the tail were mostly hidden from Italy, it should reveal itself more clearly from Mars or vice versa. Instead, the reports agree. Compact coma, no clean streamer. The geometry excuse gets thinner. Maybe the tail exists, but it is dominated by gas rather than dust. Gas can be. Questions. Post-perihelion is usually the moment when a comet shows its hand. Heating peaks near closest approach, then the released material fans out and sunlight sweeps it into structure that anyone can follow. In this case, the reveal never came. The Italian and Spanish frames were not outliers. They were the beginning of a pattern. Follow-up images repeated the same stubborn theme. A fuzzy bead of light, not a streaming banner. None of this proves the mass loss accounting wrong. The orbital fit that demands a thrust still stands, and the numbers remain persuasive. The implication, however, grows sharper. Either the ejected material was dominated by components that do not make a bright tail, or the grains behaved in an unusual way, or some part of our picture is incomplete. The quiet is not the absence of physics. It is physics we have not yet nailed down, so the reality check does what good checks always do. It narrows the field. If geometry cannot carry the whole story and dust, refuses to announce itself, then we must chase gas signatures, particle sizes, and timing with more discipline. The paradox keeps its shape. The comet lost a great deal of mass, and yet the sky does not show the expected aftermath. We hold the images up to the light and admit what they say. The tail we ordered never arrived. Anomalies are not conspiracy fuel when they arrive as measurements. They are breadcrumbs. So we pick up the first 5 and walk them in order while the evidence is still warm. The point is not to stack wonder for its own sake. The point is to see whether unrelated quirks start to behave like a pattern you can draw on a napkin. Start with the way this traveller entered our neighbourhood. 3i Atlas is interstellar, which should mean any angle it pleases. Yet its path hugs the plane of the planets within a few degrees while moving retrograde against their flow. That is like a stranger walking the exact stripe down the centre of a crowded highway while everyone else drives the other way. You can call that chance. Astronomers did the math and found a likelihood near 1 in 500. Not impossible, not comforting either. Next comes the sunward jet. Comets blow material away from the sun because sunlight and solar wind shove dust and gas outward. That is the rule. Mid-year imagery captured a feature that refused to obey, a narrow jet pointing toward the glare. Not the perspective trick known as an anti-tail. That illusion has a fingerprint that modelers know how to subtract. Teams checked geometry, timing, and viewing baselines. The sunward feature persisted. A real jet-fighting headwind is hard to square with simple radiation pressure. When a rule bends that far, you take another picture, and then another. The result stayed strange. Third is a duet of size and speed. 3i Atlas is a solid body several kilometers across and carries a mass far beyond the first interstellar visitor, Oumuamua, and the second one, Borisov. At the same time, it tears through the inner system faster than both. Large objects are rarer than small ones. Fast ones are rarer than slow ones. The combination is like spotting a blue whale sprinting. The odds do not forbid it. The odds do raise your eyebrows and keep them there. Fourth is timing that feels almost theatrical. The object brushes past Mars when multiple spacecraft are awake and watching. It skims by Venus, and later near Jupiter, at ranges that are close enough for instruments to work, yet not so close that gravity yanks the path into a new shape. Then, perihelion lands in a geometry that hides the comet from Earth, just when you might expect peak spectacle. You and I should be allergic to stories that sound planned. Still, when a tour routes past our cameras and dodges our most crowded vantage point, you pause and take stock. The fifth oddity lives inside the light itself. Spectra hint that nickel outweighs iron in the material around the body, which is the reverse of what surveys have taught us for most comets. The ratio of nickel to the cyanide family appears far higher than the usual spread, not a small tweak, but orders of magnitude beyond familiar ranges. Nickel-rich mixtures can appear in industrial alloys on Earth for strength and heat resistance. That does not make this alloyed hardware. It does make the chemical fingerprint feel foreign compared with ordinary icy dirt balls. 5 oddities down and the story starts to hum. Each piece can be explained with a special angle, or a special birth environment, or a special sequence of heating events. Stack several specials, and you begin to wonder whether there is a common root hiding under the floorboards. We do not get to declare a grand cause because our curiosity wants one. We earn that step if the numbers insist on it, so we mark what we have. A path that hugs the ecliptic while swimming against the current. A jet that points into sunlight. A body that is both big and fast. A timetable that flatters. Our cameras while ducking our best view. A composition that flips expectations. None of these is a verdict. Together, they start to feel like a rhythm. The question is whether the second half of the list keeps the beat. Now we cross into the chemistry and the light itself. The tally begins with water, the ingredient that usually dominates comet nuclei. Most classic comets are dirty snowballs with water as the main mass driver. 3i Atlas looks different. Analyses put water at only a few parts in 100 by mass, closer to rock with frost than to an ice-rich wanderer. That flips a core expectation. With little water, thermal behavior near the sun changes. Vents can be fewer and harsher. Dust lifting can stall if grains cling to a denser surface. Low water is not a headline by itself. Coupled with strong non-gravitational acceleration, it becomes a signal that something unusual powers the thrust. Next is polarization, which sounds abstract until you realize it is simply the orientation of light waves after they scatter from particles. Comets have a well-mapped polarization fingerprint that depends on grain size, porosity, and composition. 3i Atlas parts company with that library. Measurements show unusually strong negative polarization, a trend beyond the range that models tuned on thousands of observations have reproduced. When polarization goes off script, it says the grains are not behaving like the fluffy silicate and organics mix that suits most tails. Either the grains are compact and metal-rich, or the size distribution and surface coatings are outside familiar families. Light is telling us the dust, if dust is even present in quantity, is not normal dust. Color joins the case. Near closest approach, the object brightened faster than the standard playbook would predict, and the spectrum edged bluer than sunlight itself. Most comets run neutral to slightly red because dust scatters longer wavelengths a bit more efficiently. Blue is rare in these contexts. It often hints that fine particles or specific gases are dominating what we see. A quick blue surge paired with rapid brightening is a clue that whatever came off the surface did not build a long-lived dusty fan. It flared and faded, leaving less structure than expected. There is also the sky map coincidence that refuses to die in comment sections. The inbound direction overlaps within several degrees of the region, tied to the historic WOW signal detected in the late 1970s. Precision matters here. The uncertainty on that old radio source covers a patch of sky many moons wide. A several-degree overlap can happen by accident. Still, the alignment lives in the anomaly list because it is a small number, and because curiosity is allowed to notice small numbers, provided we do not pretend coincidence equals cause. By now, you can feel the rhythm. Low water content points toward a tougher body that sheds less easy dust. Polarization says the grains we do see are not the usual porous fluff. Rapid brightening and a trend to blue, say gas, and very fine particles may have dominated the show for a brief window. Stack those with earlier composition hints that nickel appears unusually strong, and an image record that never reveals a bold streamer, and the headline anomaly lands again with more weight. The comet lost a significant fraction of its mass, and yet it never wore the bright tail that physics promised. You can rescue that paradox with a gas-heavy outflow that produces real thrust and minimal dust. You can suggest that many grains were large and dropped quickly out of the scattering regime, leaving little to draw a long ribbon across the sky. You can argue that rotation and topography steered narrow jets that dispersed before they could merge into a classic fan. Each path deserves tests, and many are underway. Spectra for gas, time series for rotation, detailed modeling of polarization to nail down grain properties. None of these closes to the case today. What they do is pull the frame into focus. Water poor, dust odd, color strange, and geometry unhelpful is a consistent picture. It does not prove design or deny nature. It does say we are staring at an interstellar object that colors outside the lines in every quadrant that light can probe. The last item on the anomaly sheet remains the most visible absence, the tail that never appeared. Before we let imagination run, we give the ordinary a fair fight. Start with the gas-heavy idea. If outgassing was dominated by carbon monoxide or carbon dioxide, the reaction force can be large while the visible dust stays scarce. That would shrink a tail into near invisibility. The cost is that spectra ought to show strong gas lines, and the timing of those lines should track the orbital push. If later data fail to find the expected signatures at the required strength, the bill comes due. Next is geometry. A tail almost perfectly aligned with our line of sight will look thin and dim. That can happen for one observer. It is harder to sustain for two vantage points separated by the gulf between Earth and Mars. The cost is coordination. You need the tail pointed at both observers across different days and changing angles. Celestial coincidences do happen, but asking for days of alignment from both baselines stretches luck. Consider dust physics. If the grains were large, compact, and dark, they scatter light poorly and fall out of the classic bright fan. Electrostatic cohesion and surface sintering can also keep regolith clumped, so that vented gas slips through pores without lifting much material. This path has appeal because it fits the low water story and the strange polarization. The cost is that you must still deliver the measured thrust with minimal dust carry. That demands vent pressures and gas production rates that push the high side of natural models. Rotation can hide a lot. Imagine narrow jets that fire from a few active pits. As the body spins, each jet draws a tight spiral in space. If the bursts are brief and the rotation rate is just so, the spirals blend into a compact coma rather than a drawn-out streamer. The cost is choreography. You need active areas placed in just the right way, with duty cycles that produce the observed push while avoiding a visible fan as viewing geometry changes. Not impossible, not cheap. There is the accounting itself. Perhaps the non-gravitational acceleration was overestimated by small systematics in the astrometry. If the true push was weaker, the required mass loss drops, and the missing tail problem softens. This avenue deserves scrutiny. The cost is that multiple teams have modeled the trajectory through perihelion, using independent data, and converge on a similar extra acceleration with both radial and transverse components. To erase that signal cleanly, you need several unrelated biases to lean the same way. Forward scattering can fool the eye. Near the sun, light scatters, strongly at small angles, and can make the coma look brighter than the tail, even when dust exists. If you catch the comet at a phase angle that pumps the halo while the tail points nearly edge-on, your images will emphasize a compact glow. The cost is that as the phase angle evolves, the emphasis should flip and a streamer should emerge. When repeated observations under changing geometry keep returning the same compact look, the optical trick explanation loses power. Finally, composition. A body with low water, unusual nickel to iron balance, and odd polarization could be a perfectly natural product of a cold, metal-rich birthplace around another star. That would explain unfamiliar vent chemistry and grain behavior without any need for control or design. The cost is parsimony. You ask for an uncommon formation environment, an uncommon thermal history, and uncommon surface physics that together also land the object on an uncommon trajectory and timetable. The explanation stays natural, yet it begins to resemble a necklace of specials. None of these exits is a dead end. Each buys a slice of the truth. The problem is the tab. When one fix explains one measurement, two more measurements demand new exceptions. We are not multiplying tiny odds to scare ourselves. We are noticing how the least contrived story still requires several uncommon features to cooperate at once. The fair outcome of this exercise is simple. Conventional physics may still carry the day, but it must do so with a model that connects gas chemistry, grain properties, rotation, geometry, and dynamics in one clean arc. Anything less leaves the paradox intact. There is a reason scientists get twitchy when the word artificial enters the room. Extraordinary claims demand extraordinary receipts. Still, a fair investigation must ask whether some of the oddities could look like directional design without jumping to fantasy. Begin with the travel plan. An interstellar body arrives nearly in the plane of the planets, slips past Mars when cameras are awake, swings by Venus, approaches Jupiter, then hides from Earth near closest approach. Add the nickel-heavy signature, the low water content, the sunward jet, and the missing dust. On paper, that ensemble can resemble a dense, durable traveler built to survive heat and radiation, shedding little loose material, and sometimes pushing itself in ways that mimic natural jets. Imagine a rock and metal object with internal channels or vents that can open and close. When pointed sunward, those vents could expel material in a way that looks like a jet battling radiation pressure. The thrust would appear in the trajectory exactly as outgassing does, but the visual tail could stay faint if the exhaust is mostly gas or very fine particles. A water-pore mixture would help because it reduces easy dust lifting. A nickel-rich skin or coating would change how light scatters and polarizes, potentially matching the strange measurements. None of this proves intent. It shows a path by which measurements that look incompatible with ordinary comets could arise from controlled or engineered behavior. Now, measure that idea against discipline. If a traveler is maneuvering, there should be patterns that repeat with a purpose, bursts that align with certain viewing geometries. non-gravitational pushes that correlate with fixed orientations rather than with changing sunlight alone, light curves that show regular modulation tied to an internal clock rather than to simple rotation and heating, spectral lines that strengthen or weaken in ways that track scheduled venting rather than smooth thermal cycles. These are testable signatures. They push the speculation into the realm of predictions that can be confirmed or ruled out. Consider thermal behavior. A dense object with high thermal inertia warms and cools sluggishly. That can create outflow that lags behind sunlight in a steady, predictable way. If the flow instead arrives in crisp steps, with sharp on and off transitions, that begins to look like deliberate control rather than passive heating. Polarization can help here. Compact metal-rich grains and engineered surfaces scatter light differently than porous silicate fluff. Phase angle sweeps across weeks can map those differences. If polarization curves refuse to follow any dust model but sit comfortably with a compact, reflective surface plus thin gas, the story tightens. Communication searches are the temptation everyone thinks first. Coherent radio is easy to imagine and almost never found. A better use of time is to chase mechanical signatures that a cautious traveler could not hide. Micro-timing in the non-gravitational acceleration. Jet directions locked to body axes rather than to local noon. Recurring flares with a constant interval that does not match any plausible spin. These are subtle, but current instruments can look for them, especially while the object is still bright enough for high cadence tracking. There is also humility. Apparent tour routing may simply reflect the fact that we station many cameras around Mars and none near deep space where most visitors pass unseen. Selection effects can look like intention when the sample size is tiny. The same caution applies to the wow signal overlap. A small alignment on a large patch of sky is a curiosity, not a confession. The job is to keep that balance. Be open to the provocative path. Be ruthless about what would make it real. So here is the most honest position we can hold. A dense, water-poor, nickel-heavy body that sometimes vents sunward and leaves little dust could be a durable natural fragment born in an unusual system, or it could be a crafted traveler shepherding its mass through harsh space. The difference will not be decided by vibes. It will be decided by signatures that only one story can produce without strain. Until those signatures appear, we keep both doors ajar and let the data push us through the right one. Time to separate anchor from fog. The anchors first. Tianwen-1 delivered the closest images we are likely to see, and those frames show a compact coma without a clean streamer. Ground-based follow-ups from different vantage points repeat the same story. The trajectory solution demands a non-gravitational push around closest approach that requires major mass loss. Photometry and polarization are out of family with the historic comet library. Water appears scarce. Composition hints lean nickel-heavy compared with iron in a way that feels foreign. None of those pillars is built on wishful thinking. They are measurements. Now the fog. We do not yet know the mechanism that ties these measurements into one engine. We do not know the true particle size distribution near the nucleus, or whether the grains are compact and dark or fragile and bright. We do not know how much gas dominated the outflow, or how quickly the production switched on and off. We do not know if the missing tail is primarily geometry, primarily composition, or primarily timing, or if it is a mix that only reveals itself when modeled in 3 dimensions with realistic spin and topography. We do not know whether the 10 oddities share a single cause, or if they are a flock of unrelated quirks arriving at once. What we do have is a narrowing window to learn more. The object is racing outward now, dimming with each week. The best chance to pull high signal spectra, to watch polarization curve with changing phase angle, to time tiny wobbles in the path that betray jet directions, all of that lives in the short stretch before the visitor fades below practical limits. Teams are already using every clear night, every instrument that can still find the target against a crowded background. The goal is simple. Either vindicate a gas-heavy, dust-shy outflow with hardline detections and coherent timing, or corner the paradox until only one family of models can carry the load. This is where discipline matters. It is easy to fall in love with a favorite explanation and then massage every new data point into agreement. Resist that. Treat each clue as a coin that must be counted. If spectra climb when non-gravitational pushes climb, the gas story grows teeth. If polarization refuses every dust model, yet sits comfortably with a compact reflective surface plus thin gas that reshapes the picture. If geometry evolves and a streamer never appears from any baseline, the edge-on argument loses its last refuge. If timing reveals a clock that rotation alone cannot explain, the speculative door opens a crack wider. There is also the reality that we may not get a clean verdict. The cadence of space does not care about our deadlines. If the signal stays faint and the target drops into the noise, the mystery will harden. That is not a failure, it is a result, a durable puzzle that forces better tools next time. The point of a shared investigation is not the thrill of a dramatic reveal, it is the habit of building knowledge one stubborn piece at a time, and the honesty to say not yet when the pieces do not lock. So we hold two things in our hands at once. In one hand, a chain of hard facts that define the paradox. In the other, a short window to add the missing links before the trail goes cold. Whichever story wins will have to carry all the measurements without strain. The patient, gas-heavy comet scenario can do it if the lines and timing line up. The unconventional idea can do it if it produces signatures that natural models cannot fake. Either way, the clock is running, and our job is to squeeze as much truth as we can from the light while we still can. Pull back from the close-ups, and you can feel it. We are at the ground floor of a new branch of astronomy. 8 short years took us from theory to trend. First came Oumuamua, with a shape and a drift that dodged every tidy model. Then Borisov, which looked comfortingly comet-like yet still carried chemistry that raised eyebrows. Now, 3i Atlas inks a whole ledger of oddities at once, and refuses to wear a tail when the math insists on one. 3 visitors in one young decade, and none of them simple. That is not a nuisance. That is a pattern whispering, do not assume. The most important shift is not a specific anomaly, it is the way we approach these travelers. In the past, a comet was a seasonal spectacle, and an asteroid a catalogue entry. Interstellar objects are different. Each one is a free sample from a distant nursery with physics written into its surface and history baked into its spin. The right response is a playbook that starts the hour a new object appears. Immediate orbit fits to catch non-gravitational nudges. Rapid color and polarization to fingerprint grains before activity changes them. Spectra for gas while the target is still bright. High cadence timing to watch for jets or thrust that behaves like a clock. A whole field learning to sprint. That playbook extends beyond instruments. It changes how we talk about uncertainty. On this channel and in labs around the world, we honor 2 truths at once. Curiosity wants bold ideas. Discipline wants receipts. When data pull toward ordinary outgassing, we say so. When the numbers corner us into unfamiliar space, we say that too and keep asking. The reward for that honesty is trust. Viewers know we will not force a verdict to fit a headline. Scientists know that public enthusiasm can handle the words "not yet" without losing interest. The tools are about to level up. The Vera Rubin Observatory will scan the entire visible sky every few nights and will catch fainter and faster movers than current surveys can hold. That means the next decade could deliver a steady parade of interstellar targets. Some will be quiet rocks that draw a clean arc and leave. Some will flare and spin and spray like no comet we have met. A few may present the same stacked oddities that 3i Atlas brought to our door. With every new object, the statistics sharpen and the outliers either relax into patterns or stand out in bolder relief. Those statistics matter because they tame stories. If low water and nickel-heavy fingerprints show up often, we will build models of metal-rich birthplaces that make sense. If sunward jets repeat, we will find the geometry or microphysics that lets them happen. If missing tails become a motif, we will rewrite our intuition about dust lifting on dense, ancient surfaces. And if one day we see signatures that match control rather than coincidence, we will be ready to make that claim carefully, and only when the data can carry it. 3i Atlas leaves us with a gift that is larger than its own mystery. It teaches patience without passivity. We do not wait with folded arms. We plan better surveys, design faster analysis, practice extracting truth from faint light and noisy timing. We cultivate a community that can be thrilled by a paradox and still ruthless about methods. That is how a young field grows up. Somewhere beyond Neptune, something else is already inbound. It may be dim and slow, or small and unbelievably fast. It may carry water or hardly any. It may glow red or edge blue. What it will definitely carry is information from a place we cannot visit. When it appears, we will meet it with sharper tools and wiser questions, and together, we will push the boundary between the known and the next thing.